Hey everyone, welcome back. Last time we left off with this idea of cyclic subgroup generated by little g. So that was this thing, angle bracket little g, and it was the set of all possible powers of g. All right, so it looked like that. And I want to continue studying this. I think our last observation was that this subgroup right here, subgroup generated by little g, cyclic subgroup generated by little g, is the smallest subgroup of capital G that contains little g. And so, picking up where we left off, what we have is a definition now. So a group, capital G, is cyclic if there exists some element little g in capital G such that G is equal to the cyclic subgroup generated by little g, right? So when this occurs, when there's some element little g in capital G, so that when you look at this set, which is all possible powers of little g, it fills out the entire group. When that happens, we say that capital G is cyclic. When such an element exists, when a little g exists, and when such a when such a little g exists, we say that little g generates capital G, or that G is a generator of little g. Some examples, and there's some familiar examples of cyclic groups. Z is cyclic. Now let's see, why is that? Well, for this to be true, we need to be able to produce some element of Z, right? That is the generator. And so, why is that true? Well, the cyclic subgroup generated by 1. Think about what that is now. We have to work in additive notation. So all possible elements that fit this form when the operation is addition, well, there's 1 plus 1, there's 1 plus 1 plus 1, 1 plus 1, and also the negatives, right? So the cyclic subgroup generated by 1 is equal to Z, and it's also equal to the cyclic subgroup generated by negative 1. Right? You just have to remember that all possible powers in the additive setting means all different ways that you can add 1 to itself and its inverse to itself. Another example, who else? How about Z6? Z6 is cyclic. And who are some generators? Well, 1 is a generator. Another generator is 5. Right, so 5 plus 5 plus 5. If you look at all possible sums that you can do with 5 and its inverse, right, that will fill out all of Z6. So let's see, another example that I want to look at. Let's let V be the group defined by, and I'm going to write down the table for this one. So I guess I'll just use the elements E, A, B, and C. So E, A, B, C, E, A, B, C. So this is a group with 4 elements. And let's see, E, A, B, C, E, A, B, C. And then I can't read this, A, E, C, B. A, E, C, B. Oh, I see. Okay. And then B, C, E, A, B, C, E, A, and C, B, A, E. C, B, AE. So this, you wrote out this Cayley table or this group table in your last homework 1. And so the question is, so let's call this group V. The question is, does this give us a cyclic group or not? Is this group cyclic? And before I go any further, V has a name, so this is called the Klein 4 group. Right, so this is a group that we'll come back and visit fairly often. All right, so it's going to show up. And so let's answer this question now. Cyclic or not? If it's going to be cyclic, then there is some element in there so that when we look at all possible powers of that element, it gives us all of V. So let's think now, well, so let's just look at the cyclic subgroup generated by E. Well, that just consists of E itself. The cyclic subgroup generated by A, well, it's going to have A, and then A squared is the identity, A cubed is A. So the powers of A are either A and the identity. Cyclic subgroup generated by B, well, let's see. B times B is also the identity, and so it consists of B and E. And then the last one, if we look at C, the cyclic subgroup generated by C, well, that consists of C and E. So now I've run through all possible elements of the group, looked at the cyclic subgroups generated by each of them, and in no case did I get all of V. Right? So our conclusion is that V is not cyclic. In that in that homework problem, you were led to conclude, I want to say it was problem number 20, I think, on page 45 or 46. It was one of your homework problems. And that problem said, or it led you to the conclusion that there's exactly 2 groups of order 4 up to isomorphism. Every group is isomorphic to one of the 2 groups that you wrote, or one of the 2 groups defined by the tables that you wrote down. And so one of them is this group V, which we call the Klein 4 group. There's also Z4, right? So let's say it like this. On the other hand, Z4 is cyclic. Why is that? Well, there's a generator 1 is Z4. Also minus 1 is 3, so the inverse. So it's like that. So what that tells us there are 2 groups of order 4, the cyclic one and the non-cyclic one. And the cyclic one is isomorphic to Z4, or all cyclic subgroups of order 4 are isomorphic to Z4. All non-cyclic ones are isomorphic to V, the Klein 4 group. Couple of observations, I guess we could say. Oh, let me just put it right here. So examples, Zn is cyclic for all natural numbers n, and also U sub n. Remember, that is the group of complex numbers, the solutions to the equation x to the n equals 1. This is also cyclic for all n in n. All right, so the group of roots of unity is cyclic. Okay, now cyclic groups are sort of our first important class of groups that we're going to study, and we want to study this in detail. So what we're going to do is start a new chapter here, focusing entirely on cyclic groups. All right, so this is chapter 6, cyclic groups. One piece of terminology, so let's let G be a group. And let's take some element, so let's say and little g in capital G. The order of little g is the order of the cyclic subgroup generated by little g. And the notation, we'll just write absolute value bars around little g. Some other authors do this, so they'll just write like little o of g. Both of these mean the same thing. So what is the order of the element little g? It is the order of the subgroup, the cyclic subgroup generated by little g, which is then the cardinality of this subgroup as a set. So for example, in Z6, let's look at the order of 2. Well, okay, so I should do a little bit of work here. So what do I need to do? I need to look at the cyclic subgroup generated by 2. And who is that equal to? Well, you can easily compute, right, that the cyclic subgroup generated by 2, it's going to have the identity. It's going to have 2. It's going to have 2 plus 2. It's going to have 2 plus 2 plus 2. Remember, we're working in Z6, so the operation is mod 6. And so 2 plus 2 plus 2, oh, that's 6, which is 0. And so it turns out that that then closes the cycle off. So the answer is 3. The order of the element 2 is equal to the order of the subgroup generated by 2. Right? That subgroup has 3 elements, and so it's the order of the element is 3. Another example, in GL2R, the order of the element -1001 turns out to be 2. Now, how would you do this? Well, you'd look at what happens when you start multiplying this matrix times itself. And if you do this matrix times itself, you'll get the identity matrix. And then if you do it, if you raise it to the 3rd power, you'll get the matrix again, this matrix. And so the elements in this subgroup are exactly the matrix itself and the identity matrix. And so these two right here are equal. This is the subgroup generated by that matrix right there. All right, so its order is 2. Oh, one more example. In Z, the order of the element 3 turns out to be infinite, right? So what you do, you keep adding 3 plus 3 plus 3 plus 3. You can go on forever. So the subgroup generated by little 3 is an infinite subgroup of Z. Right? In fact, you can show that it's all multiples of 3. All right, so reason the cyclic subgroup generated by 3 is equal to the set of all multiples of 3, right? And that is the set, well, to go dot, 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 -3, 0, 3, 6, blah, blah, blah. All right, it's all possible multiples of 3. That's an infinite set, all right, which tells us the order of that element is infinite. Okay, now important for our study of cyclic groups is the following theorem. And this is the theorem, you probably learned this theorem in Math 248, but we want to just remind you how it goes. So this is going to be theorem 6.1. It has a name. It's called the division algorithm. And so the statement goes like this. Let's take a couple of integers. Let's call them m and n. So let m and n be in Z. And we need one of them to be positive. So let's say m. So where m is greater than 0. Then there exists unique integers, which I'm going to call Q and R, such that n is equal to Qm plus R, and 0 less than or equal to r strictly less than m. Yep. So what is this result saying? That there is, every time you choose an integer and divide it by a positive integer, you can find a q and an r uniquely that satisfy that equation right there. So, and then we're going to prove this, so let's see how the proof goes. So I want to form a certain set, and I'm going to call this capital S. So S is going to be the set of all elements, all integers of the following form. So it's going to be n minus ma, where a runs through all integers that make n minus ma greater than or equal to 0. Right? So take all, we've got an n, we've got an m. Those are fixed. Look at all possible integers a, create this, all possible integers of this form right here, but we only take the ones that are greater than or equal to 0. We lump all those together in this set S, right? So there's our set S. Now, if 0 is in the set S, then what we're saying, right, is that n minus ma is equal to 0 for some choice of a. Right, so then there exists some q in Z such that, well, so what do we have? N minus q, m times q equals 0. And so n is equal to, how do I write it? Qm plus 0. Right, so in this case, we've got our q and our r is 0. Okay, so there's the first case, and then we'll consider the case where 0 is not in there. So if 0 is not in S, we can find some A. So let's we can find A in Z such that n minus ma is strictly greater than 0. So we know the elements in this set right here are non-zero, or are integers that are greater than or equal to 0. If we know that 0 is not in the set, right, that means then that all such elements in here are positive, right? Now, this is just sort of common sense now. You can, as you run through all possible A's, you can certainly, it doesn't matter who n is and who m is, by choosing A correctly, you can create an expression of this form that's strictly greater than 0. So, and all I'm getting at, so I can say that is, S is non-empty. There's at least some element in this set S, right? Just find the right A. And depending on who n and m are, it's, you'll have to choose A differently, right? But you can certainly find some choice of A that gives us a positive output for that expression right there. Now, since S is a subset of the natural numbers, so how do we know that? Well, we know that S does not have 0 in it, so S is made up of positive integers. We know that it's non-empty, so you need to remember now a theorem or a principle that tells us something about if you have a non-empty subset of the natural numbers, right? The well-ordering principle tells us that this set S has a least element. So since S is a subset of the natural numbers, there is a least element, and I'm going to call that, what's a good choice? How about R? And that's going to be n minus qm. So in S, there is a least element. Its name is R. And, okay, all elements of S are of the form n minus a times m. And I'm just saying, okay, the one that realizes R, the choice of A, or the A that gives us R, let's call that Q. All right, so Q is the integer that makes this equation true. So suppose that R is strictly greater than m. Oh, sorry, no, actually I wanted to say greater than or equal to m. So suppose R is greater than or equal to m. Then I want to look at n minus m times q plus 1. And I guess let me put the q plus 1 on the other side. So it's really q plus 1 times m. That's equal to n minus qm minus m, which is equal to, oh, now notice n minus qm, that's r. And r minus m is greater than or equal to 0. So what does that tell us? So it tells us then that that this element right here is an element of S, right? It is of the form n minus integer times m, right? That's what elements in S look like. So we can say, and so n minus q plus 1 times m is an element of S. It is of the proper form to live inside S because it is n minus an integer times m that gave us something that's greater than or equal to 0. But if we look at n minus q plus 1 times m, how does that compare? Well, this element right here is strictly less than n minus qm, right? Because of this q plus 1 part, knowing that m is a positive number. This is a contradiction, right? So contradicting the fact that R, which is n minus qm, is the least element. Of capital S. Okay, so what does that tell us then? Well, that tells us that R has to be strictly less than m. So therefore, m is strictly, I don't want to say this, R is strictly less than n. And we also knew, because R is an element of S, that it's greater than or equal to 0. And so we have the desired restriction or restraints on our element R. So that proves the existence of the elements R and the Q. There's also in the division algorithm, there's the uniqueness statement, and I just want to leave that as an exercise. It's not particularly difficult. If you've taken Math 248, you can just look back at the notes from, if you took it from me at least, probably any Math 248 class, you learned this theorem right here. It's worthwhile just going through the proof and understanding how this proof goes. You should work out the uniqueness on your own. Okay, but now we can make use of this thing called the division algorithm. Okay, now that we have the division algorithm, we can start exploring cyclic groups. And so our next result, right, so this is theorem 6.2, goes like this. Let G be a cyclic group if H is a subgroup of G, then H is cyclic. So you can paraphrase this theorem like this. Subgroups of cyclic groups are cyclic. Anytime if you have a group or a certain type of group, right, one of the interesting questions, one of the things that you want to know about the group is what is the nature of the subgroups? And so this theorem tells us something very powerful. It says if you start off with a cyclic group, you can't have any subgroups except other cyclic groups, right? So subgroups of cyclic groups are cyclic. And the proof is kind of fun. So let's go. Let's see. G is cyclic, so it's got to have a generator. So let's let little g in capital G be such that the subgroup generated by little g is equal to big G. Right? So we've got a generator for capital G. Now, if H happens to just be the trivial subgroup, then of course it's cyclic, right? So then H is the cyclic subgroup generated by the identity, and we are done. So we're just getting the case of the trivial subgroup out of the way. Otherwise, what I want to do is consider the following set. So this is going to be the set of all natural numbers such that G to the N is an element of H. Is that right? Yeah. Okay. Now, thinking about what H is a bunch of elements sitting inside capital G, right? And so, what do the elements of capital G look like? They look like powers of little g. And so, for some positive power of little g, it's got to land inside H, right? We know that H is not just the identity, so it's got to have some powers, right, that are non-trivial powers, right? Something other than g raised to the 0. Right, so since G to the N is an element of, or let's say is in this set, nope, said that a little bit weird. So since G to the N has to be an element of capital H for some N in natural numbers, we see that this set is non-empty. So what do we have then? We have a non-empty subset of the natural numbers by the well-ordering principle. We have a least element. Call that least element little n. Right? So this set right here has a least element. Now remember what we're doing. We are trying to show that H is cyclic, which means that we're trying to produce a generator. We need to produce a generator for H, right? To show that H is cyclic, we need to show that it has a generator. And the claim then is that a generator is found by taking the generator for capital G, so take little g and raise it to the mth power, where m is the least element. It's the smallest positive integer. So that when you raise g to that power, it lands inside H. And it turns out that this is going to be a generator for H. So to prove this claim, let's first note this. So since G to the M is an element of H, note that G to the M raised to the kth power, do I want to use K? Actually, I want to use an N in this case, so because I'm going to use K in a second. g to the m raised to the n is an element of H for all integers n. Why is that? Well, it's because H is a group, so it's closed, right? Which means that g to the m raised to any power, right? Since g to the m is in H, any power of g to the m also has to live inside H. Now, what did that do for us? Well, so it follows that the subgroup generated by g to the m has to be a subgroup of H, right? All possible powers of g to the m live inside H. So what does that mean? Well, we're trying to show equality, and what I've done so far is I've shown that the right-hand side is a subset of the left-hand side. Now I need to do the reverse inclusion. So now I'm going to pick somebody in the left-hand side and show that it lives on the right-hand side. So now let's let X be an element of H. Okay, now what does X have to look like? Well, let's see. X is an element of capital G, which means it's the power of little g. So then X equals G to the K for some K in, well, okay. Officially, it needs to be in the integers, right? X is some power of little g. But if g to the k lives inside H, then so does g to the minus k. Right? So I'll say it like this. Note that g to the plus or minus k then has to live inside H. And so we can just assume that little k is actually a positive number. And so we can assume, I guess I don't need to be positive, I just need to be greater than, so we can assume that k is, it's got to be greater than 0. So why is that? Well, because if k was negative, then negative k would be greater than 0, and so that would be the one that we put in H, right? So we can just assume that we chose k to be the positive one, and then negative k would be the inverse. Okay, so we can assume that k is greater than 0. In this case, it follows that k is greater than or equal to m. Now, why is that? Well, we have a least element, m, right? And so anytime if we have a positive integer, so that g raised to that positive integer lives inside k, that means that k has to be greater than or equal to m. And so the reason is that m is, or let's just say by minimality of m. Minimality of little m, right? So k has to be greater than or equal to m. So now what I want to do, well, what do we have now? And what am I trying to do? So let me just over here remind you. So we're trying to show that H is equal to the subgroup generated by g to the m. Which means, right, we know that x equals g to the k. What we need to do is show that k is a multiple of m. Right? So that's our job. What we really want to do is show that g, or that x, we need x to be g to the m raised to the n. So I need g to the k to equal g to the m times m, which means that I need k to be a multiple. Okay, so now here's what we're going to use. So by the division algorithm, we can write n equal to qm plus r, where q and r are integers, and r is greater than or equal to 0, but strictly less than m. So what does that tell us then? So x is equal to, well, it's g to the k. Oh, crap. Sorry. One mistake. I should not be writing n here. I don't have n, I have a k, right? So I need to have a k right there. Sorry about that. So replace that n with a k. And then, right, so I'm running the division algorithm on k, not n. So x, that's equal to g to the k, which is equal to g to the qm plus r, which is equal to g to the qm times g to the r. Okay, so we've expressed x as g to the qm times g to the r, and we might as well just write this. So this is g to the m raised to the q times g to the r. So now, g to the r is equal to x times the inverse of this. So I got to multiply on the left. It's going to be g to the m to the minus q times x. So what did I just do? I took this equation, I have x equal to this thing, I multiplied on the left by the inverse of g to the mq. That allows us to say that g to the r is of this form, and notice this element is an element of h, this is an element of h, and so that tells us that this element is that g to the r is an element of h. I guess I should put it up right here. All right, so that element is in H. Fine. So what do we know? We know that R is greater than or equal to 0, but strictly less than M. Since R is strictly less than M, we conclude that, well, what does that tell us? Well, m is the least positive integer, so that g to the m lives inside h. So here we have g to the r living inside h. Because of the minimality of m, that forces us to conclude that r is equal to 0. So we conclude that r equals 0. Therefore, x now can be written as g to the m raised to the q, right? And that is an element of the cyclic subgroup generated by g to the m. Thus, so what does that tell us? That shows that H is a subset of the cyclic subgroup generated by g to the m. So that finishes the proof of the claim, right? So we can say claim done. And that's really all we needed to finish the proof, right? So now we have shown that H is equal to the subgroup generated by G to the M. All right, so our conclusion, H is cyclic, right? And that is the proof. And I'm just checking the time here. Yeah, you know what, let's finish off with one last, well, just kind of a quick corollary to our theorem. So it's theorem 6.3, or corollary 6.3. If H is a subgroup of Z, then H is equal to N times Z for some integer N. And the proof, the cyclic subgroups of Z are of the form subgroup generated by N, and what this means, right, those are all integer, all integers that are multiple of N. And so by theorem, by our previous theorem, so by theorem 6.2, these are the only subgroups of Z, right? Z is a cyclic group, so it only has cyclic subgroups. Cyclic subgroups look like this in general, but in our particular setting, right, subgroup generated by N is a set of all multiples of N. Right? So that completes the proof, and so that characterizes all possible subgroups of Z, right? All subgroups of the integers are multiples of integers. Right? Okay, so that's a good place to stop. We will pick up with continued study of cyclic groups. In fact, we have a good deal of work to do. It's going to do some hard work, all right, to get a full handle on subgroups of cyclic groups, but that's where we're headed. Okay, so we'll see you next time.